Good morning, everyone. We're going to start chapter 5. We did started this one before. I'm going to just continue on some example of the practices that we are doing. Yes, you have a question? Did you have a question? Oh, I see. Raise your hand. So there is, before we go further in this chapter, so I'm going to just again bring your focus on what's the purpose of this chapter. If I can have your attention, please. So we are discussing isothermal reactor design with respect to conversion. This is again chapter 5 of your book. So just to strategically look at this, how we approach this problem. So we define 5 steps. Okay. So step number 1, I'm going to just have all these examples to this one and show you how to do it. Step number 1 is mole balance, which is basically chapter 1 and 2 of your book. And then we have step 2. Remember what was step 2? So step 2 has to do with the kinetics. Basically, it's the rate law, which was the focus of chapter 3. Again, in chapter 7, we are going to again look at the kinetics and show you how we analyze the data, the experimental data, to get the kinetic parameters. So step 3. Step 3, we have stoichiometry. Stoichiometry, and that was your chapter 4. So we made the tables and so on and so forth to get the relationship between the concentration and the conversion. And step 4, step 4, you combine them. You combine all this equation. Again, there is a catch here. So the combining is when you want to solve the problem analytically. You want to solve it by hand or calculator. So you just do these steps as combine everything in one equation. However, if you use the polymath, just leave it as it is and then introduce the equations to polymath. You don't need to combine them. Basically, polymath likes to have equations as it is, and then that it will do the calculations iteration for you, right? So when we say combine, means when you want to have an analytical solution, you want to solve an equation, so you would do together. Otherwise, you just leave them as it is and introduce them to software that you are using. And step 5 is evaluation. Evaluation means solving this equation. So to do that, we can do it analytically. Means solving the equation mathematically, or graphically, or numerically, and the last one is using a code or software, such as using software such as Polymath or Console and other softwares in that fashion. So these are the different steps in solving a problem to design a reactor in isothermal conditions. So as I mentioned, the focus of this course is mainly isothermal, means the temperature of the reactor remains constant. However, towards the last 3 chapters of this book, chapter 11, 12, and 13, it talks about non-isothermal, which is mainly beyond the subject of the course, although I like to touch it if I have time. So for that one, you introduce another steps here, like between step 3 and 4, and that would be energy balance. So the energy balance of the reactor relates the concentration and K and other parameters to the temperature, and then shows how temperature influences these parameters, and then you have another equation added to this one. That's what it is for non-isothermal. Okay, so we're going to just practice these 5 steps. Although, I mean, after a couple of times that you do the exercise, it gets very routine. So you might not just have a step 1, a step 2, a step 3, but this is what we do basically. Just a strategy that we follow to solve the equations, right? So I did an example last lecture. And I'm going to just follow up on that example, but a different reactor. So if you remember, look at your notes. We had A plus B gives 2C, and we looked at it for isothermal reactor design, and we looked at it in a CSTR, correct? And that's what the conversion we got from this previous one, 0.75. So we're going to repeat this once. Again, the example is A plus B gives 2C with the exact data of previous example. And we're going to just find the conversion, this time for plug flow reactor. Okay? So any question with respect to these steps? So example. So following up with previous example, but in plug flow reactor. So the previous example was in a CSTR, so exactly the same data, but this time in plug flow reactor. Okay? So I'm using the same data. I'm not going to put it here, so just looking at your notes. So basically, the reaction was A plus B gives 2C. And just to to remind you, was 1 molar and 51.2 molar of the acetic anhydride and water, and then we had the K, and that was it. So we had to calculate the conversion of the reactor. Now we are doing exactly the same, but with the PFR. So it would be a good comparison as how we are doing it. Okay, step 1. Step 1, what is the step 1? What is it? Mole balance, right? Okay, so just a small cartoon here. Just was is a PFR. It goes here, so we want to calculate X, and so is I guess 0.00324 liter was input, if I'm not mistaken. Yes, 0.00324 liter per second. Liter per seconds. And this is a PFR. So step 1 is the mole balance, right? Mole balance. So without looking at the notes, you know what is the mole balance for PFR? dx over dV. So this should be now your second nature, right? So you don't even need to look at the notes. Also, we provide these equations for you for the exams. I mean, we are going to provide a single cheat sheet, so you don't have to bring anything. But similar to quiz, the midterm exam will be open book, so you can bring your book only, not the notes, in case you want. So sometimes people like to have the book beside them. It's a psychological effect. So, but as I said, you can do the exam without even bringing anything, because we provide all these equations for you. So it would be minus RA FA0. Right? This is the design equation for a PFR. Step 2. Step 2 is rate law, right? So if we don't provide you with the different kinetics, so you consider that this is the elementary reactions, meaning that it follows the stoichiometry. So it would be minus RA is K CA CB. Step 3 is a stoichiometry. So for this case, what is the case? So you have to look at it, either it's the liquid or it's the gases, or look at the conditions. Obviously, if there is liquid, right? So already you have a simplified version. So you have relationship between the concentration and conversion. If there is gases that the mole doesn't change between left and right, so your delta and epsilon are 0, again you are in the easiest start. Or if your reaction is happening in a fixed batch reactor with a fixed volume, doesn't matter even if the mole changes, because the volume is constant, V equals 0, correct? As long as, because I mean sometimes the vessels can be like an expandable volume, so has like a piston and cylinder, so that for that one volume changes. But if there is the fixed bed, if it's a batch reactor, so the volume is constant, right? Even if the mole changes. So these are the things that you need to have in your mind. Otherwise, you just simply just follow the calculation for epsilon and delta and find it. For this case, we have the easy equation. So it's CA is CA0 1 minus X, And if you look at the course notes, we mentioned that this one, CB, what would be if we don't simplify to CB naught? So we mentioned that because it's a very large volume, we consider this one to be CB0. But otherwise would have been like, if that was not the case, so CB would have been CB0 times X. So, but depending on what is the theta, that can be 1 or 2 so, of the X. So it would be a fraction of the ratio of the conversion is produced. Obviously, if there are 1 to 1, would be CB0 times X. Okay, so step 4. Step 4, we are going to combine these equations. Combine. Again, keep in mind, again, if you do it analytically, you need to combine. If you use a software, you don't need to combine this equation. So to combine, so would be minus RA K CB0 CA0 1 minus X. So we said that these two can be constant. So would be another constant, I would call it like K prime, would be K prime CA0 1 minus X. Okay, so then is solving the ordinary differential equation. So it's going to be dx dv is minus RA divided by FA naught, and that would be K prime CA0 1 minus X CA0 V, and then if you isolate the terms, so it would be dx over 1 minus x, and that would be K prime V0 dV, and I mean dV over V0, you know that is the definition of tau. So tau is from chapter 1 was V over V naught. So d tau would be dV over V0. So therefore this would be K prime d tau. So it's easy to integrate. So it's ln 1 minus x minus ln 1 minus x would be K prime tau, and you need the initial condition or boundary condition to solve this one. So easily you can solve it. So I'm going to just flip to the next page. So you write this one.
Sorry, where does the CA naught and CA?
I beg pardon? So this cancels out. You see, we have CA is close, so we have CA0 here. CA. Okay. Yes, please.
I just want to confirm that the bottom, so V naught is a flow rate, but then dV is volume rate.
Yeah, V is the volume, and V naught is the volumetric flow rate.
Okay. So then the dV is the volume.
dV is volume, right? Yes, volume. This is volume. Any other question? Then what you do the next stage, you just integrate this one. So integral of this one would be minus ln 1 minus x, and this one is K prime tau. and then you need to apply your condition and solve it. So I'm going to do it just for the sake of doing some exercise. Okay, so with the so your V down here. So ln 1 minus x would be minus k prime tau, and from here you can find x to be 1 minus e minus k prime tau. Okay, so we have tau is V over, again, volume over volumetric flow rate, which is 0.311 liter over 0.00324, and that would be 96 seconds. So if you calculate here, x is going to be 0.61. This would be your conversion for this case.
How do we get a negative there for the K prime?
That's from the integration, minus ln. This integration?
Okay. Okay.
So the next example, I'm going to do another, as I said, basically the course, the chapter 5 is just these steps. There is not new formulation is introduced. Basically, you are trying just to show you how to solve it. Basically, it's a bunch of exercises. Otherwise, the chapter is done. So you can go to the next chapter if you want. I can finish the whole book if you want within 1 month. Not rushing through it, but just to. Do you like that? Let's try this one. Last time, I mean, last 3 years. This is the 3rd year I'm teaching this course here. So we just had kind of towards the later in the class, I had some struggling with the time just to catch up with at least what I wanted to present, because we did a lot of examples and exercises, which obviously the students like it. The majority of the students like it. But if you like this course is the guy Scott Fogler is kind of a friend. I know him. He's a professor at the University of Michigan. And we just sometimes we chat over the phone, and he uses the PowerPoint presentations for this course, and I guess you might even find it online. And there is a 24-25 PowerPoint presentations, and this presentations basically covers the whole book. And the first year I was just chatting during the course where you are, where I am, and then I said, I was just chapter 3, and I said, where are you? He was already chapter 7 and 8. And he said, what you guys are doing there? And he was just kind of saying that perhaps maybe you have better students, but I said, no, it's not this, because you're rushing into the course anyway. So, yeah, so no, by no means they are better. But the thing is that that's the way he presents. So he uses you can if you use the PowerPoint, you can paste through all these materials and do this one. It's not a difficult task. Anybody have a question to it, or somebody have the hand raised? No, you have a question? No, okay. So. This another example that's with. So if you want less examples, let me know. I can provide these ones in D2L. Do you like the majority of class? Do you like these examples, or do you want me to cut it? It's not boring. If it's boring, let me know. No, it's just anybody feels boring. No boring. So you should do it, right? It was okay, so we do it as much as we can. Okay, the next example is a gas phase reaction. Gas phase. So is 2NO is a decomposition of 2 NOCl to 2NO plus Cl2 plus Cl2. This is happening in a PFR, a plug flow reactor. Okay, so some data we have. This data is like V0 is 10 d-meter cube per second. K is 0.29 d-meter cube per mole seconds. Ca naught is 0.2 molar. When we say M, capital M means mole per liter. So liter. So basically, you say M, capital M, which is mole per liter or mole per d-meter cube. So then we have isothermal condition and isobaric. So P and T remains constant. What else? And we have X is equal to 0.9. So what we're calculating? So we're calculating the volume of the reactor. Okay, so I'm going to just again follow our strategy. Step 1, 2, 3, 4, 5, and we solve it. By the way, I just I'm going to assign some office hours. So as you wanted, Monday from 1 to 2 and 2 to 3, I guess I have to check with my. I'm going to email it to you today. So that would be 1 to 2 with one TA and 2 to 3 to other TAs. So they are in ill building. Well, they must be available for this time, but if you want by any chance to see them, just send an email. Just make sure they are there, but definitely because it's office hours, they will do their best to be stick to their desk for this hour. But that doesn't mean that you can come only in this time. Anytime you have any questions or concerns, so you can email us. I mean, they are more available than me, but even you can email me. Then make an appointment and come. So it doesn't have to be Monday afternoon, okay? Especially, I guess, for midterm and final, usually students are in demand of extra hours when it gets to the exams. So by all means, you can come and see us. And check your D12. There are lots of materials uploaded there. The questions, problem sets, even the lecture notes. I don't know how this camera is doing it. This is the first time we are doing it in this class. So we are uploading to the YouTube, but directly to D12. So you can see that one. And the other class, the tutorial is the easier way because it's, the video camera is directly connected to this document camera. It's easier than that one. I guess there is a better quality. Okay, step 1. Solution. Step 1, always with the design equation. We have a PFR. So we just did it in previous example. dx dv is minus RA FA naught. Step 2. Step 2 is rate law. So minus RA is KCA squared. It follows the elementary type of reactions. Step 3 is stoichiometry. So this is the difference between this example with the previous one. So we are dealing with the gas phase, and the reactor is a flow reactor. It's not a batch reactor, and the number of moles is changing. So therefore, your volume is changing. That's the difference between this example and the previous one. So we have to calculate the V and incorporate it into the concentration equation. So if you remember, our V0, V was V0 1 plus epsilon x, and that's going to be in the numerator of the equation. So your CA in the previous example was CA0 times 1 minus x. In this equation, your CA is CA0 1 minus x divided by 1 plus epsilon x. Right? This term is additional one. And this because of this. Yeah.
From the last equation, last example, why do we not have that part? Is it because it was liquid?
I guess it was liquid, right? Let me just check. Yeah, it was liquid. So if it's the cases, again, just to reiterate, if it's liquid, if it's gas in a fixed chamber, it's a batch reactor, or if it's a gas with constant number of volumes both sides, epsilon would be 0, basically doesn't count. So it would be easier pathway. Otherwise, you have to consider that one. And where does this V0 goes here? What happens to this V0? Vanished. But the way that it vanished, because we have a FA0 in the numerator, so FA0 divided by F0 becomes CA0, right? That was it is. So basically CA for the flow reactor is FA0 times 1 minus x, right? And FA0 divided by V0 is CA0. So that one and CA0 1 minus x, 1 plus epsilon x remains there. And the fourth step is combine them. Step 4 is minus RA minus RA is K CA0 squared 1 minus x squared divided by 1 plus epsilon x squared. So after that one, you have to evaluate it. Again, we try to do it analytically. Therefore, this combination is helpful. I'm going to flip to the pages. Okay, so then the next step is introducing a ordinary differential equation. Is dx over dv is k CA0 squared 1 minus x CA0 V0 1 plus epsilon x squared. So if you just go through the integration, so would be 1 plus epsilon x. So there is a table of integration in the appendix of your book. So you can look at it. Dx is equal to k CA0 V0 dV. So this is from 0 to V. This is from 0 to x. Okay. And if you do the if you do the integration, that would be K CA0 tau, and then the other side would be 2 epsilon, 1 plus epsilon, ln 1 minus x plus epsilon squared x plus 1 plus epsilon squared x 1 minus x, that would be equal to, that would be the left hand side, equal to K CA0 tau. Okay, so you need, what you need to do now, calculate the epsilon. Epsilon is the, as I said, the moles of the production minus the moles of the reaction divided by the number of moles, and multiplied by the mole fraction. So mole fraction of A naught times delta, and that would be 1. If you calculate delta, you see that it's going to be 1/2. And we had x equal 0.9 in this equation. If you put these values, and x was 0.9, if you put these values into this equation, your tau is going to be 294 seconds. And from here, you should be able to calculate volume of the reactor, which is V naught times tau, and that would be 2940 liter. Yeah.
I think in the first line it will be 1 minus x over 2 dx dv.
For less power to optimize.
I beg pardon?
The first part, 1 minus x, should be power to provide power to.
Okay, so you're talking about
First
first line? Here?
Yeah.
Oh, yes, so would be there is a 2 over here too. Okay, so let's do another example. The next example is dealing with the gas phase in a batch reactor. Okay, so let me just start, and then if you finish, otherwise I will do it the next lecture. So, example. So we have a gas phase reaction, which is 2A, for example, 2A gives 2B plus C, and this is taking place in a batch reactor. So we want to calculate the time that certain conversion is taking place. So I go through the steps that I introduced. So the first one is step 1 is the mole balance for the gas phase for the batch reactor. So it would be dx dt would be minus R A V naught over NA0, correct? The question is this gas phase reaction is taking place in a batch reactor. So we want to calculate the time that certain conversion is taking place. Basically, a relationship between the time and the conversion. So the conversion is 0.9. So basically, the question would be, find the time that you achieve 90% conversion. 90% conversion. You want to find the time is a batch reactor that this gas phase reaction is taking place, that the 90% conversion is taking place. So as you know, the time is changing, is not a steady state condition in the batch reactor. So you have your reactants in a vessel, and you let the time passes by. So the reaction takes place, and as time passes by, your conversion increases. You have the highest rate at the beginning, at the middle, at the end. So how the rate changes in the reactor? If you plot the minus RA versus time, how your rate appears to be, the plot. Conversion increases. If the time passes by, and you don't see it here, in a batch reactor, if this is a conversion, right? This is time. The conversion goes like this, generally speaking. So it goes there and then levels off. And if you are talking about the rate, how the rate changes, at time 0 when the reaction starts, you have the highest rate, and then as the reaction proceeds, the rate drops. So basically you have like this for rate. And if you look at it, when we were plotting the FA0 over minus RA for Levenishvili plots was the other way around. So it was something like that. So because minus RA is in your denominator. This is a typical one. For this case, that might be it follows the same trend, but might be a different graph, obviously. But in the batch reactor, that's what is happening. I mean, generally speaking, for the reactions, you anticipate have the highest rate at the beginning, unless the reaction is auto-catalyzed. What does it mean? That as products are produced, that product is becoming catalyzed for the reactant. Like at the beginning, you have a certain range, and as you produce the product, this product is coming and reacts with the reactor. And then you have a higher rate. Autocatalytic reaction goes to a peak and then comes down, the rate. Right? So, but generally speaking, if it's not the case, you have the highest rate at the beginning. And then as time passes by, your reactants are consumed and your rate drops. Okay, so we're very in more balance and rate now, okay? So step 2 is going to be the rate now, which is the minus RA is K CA squared. I'm going to write the stoichiometry and then solve it next lecture. So step 3 is your stoichiometry. So what's the stoichiometry here in this case? So look at you have gas phase, you have batch reactor, you have a change of the moles. So what is the stoichiometry here?
CA naught 1 plus X, 1 plus epsilon X.
What is epsilon here?
Epsilon is 0.
No, we have the change of the mole, but keep in mind, we are dealing with the batch reactor. For the batch reactor, we have V is equal V0, right? In a severe case, you might have change of the pressure in the batch reactor, but unless you don't have the data, you don't take into consideration. Because if the volume is constant and you have a big change of moles and things, so your pressure might change. But that might not be very big. So if it's negligible, so we don't consider it. And we don't have that data to consider that one. Because the change of the volume is not only because of the epsilon, it's also due to the temperature and pressure, right? So temperature, as I said, most of the time in this course we are dealing with isothermal. But pressure, we don't know. If there is no information about the pressure, so therefore you consider the volume to be constant, and your CA would be CA0, 1 minus X, and so then I have to the next step is to combine this one, which I do it in the next lecture. So this one is an example of the batch reactor and gas phase, and calculate the time. Before we switch the class, any questions?